Okay, just a quick video. As you can see, I cleared the deck here, just shoved everything aside. I'm in the middle of this Marantz 510M restoration video series. But I got an interesting email from one of my patrons, and I thought it would be better to just do a video for all of you real quick. So this is not scripted, and I just kind of threw it together, so it is what it is. A lot of you have asked about the two things keep coming up again and again. The use of an isolation transformer on your bench to isolate the mains coming into the house from your device that you're testing, and we'll get a little into that here in a second, and how a current limiting tester works, a dim bulb tester where you use a light bulb filament to limit the current of the device you're testing. And I get a lot of questions about the odd looking setup that I have in here. Turn my flashlight on, you can kind of see a little better in there. And if I turn it on, you'll see the little meters light up and things. But what is it and how does it work and why do you need it? And that's what I hope to answer in this video. So first, a little bit of kind of a backstory, why we need this in the first place. And that is whenever you connect something to your mains power. So you see this little diagram that I drew here. You have your utility pole that's on your street, and this is for the United States. So this is, other countries are going to be a little bit different, and the voltage levels and so forth are going to be different. But power distribution is very similar, believe it or not, throughout the world. So you have your generation plant where the power is generated, however they do it. And then that power is stepped up to very high voltage. So they go to very, very high voltages, sometimes in the hundreds of thousands of volts. And that's called your transmission line. So whenever you see like those three wires that are way, way high up at the very top of your utility tower or utility pole, those are usually transmission lines, and those are going to be the highest voltage. They can be up in the hundreds of thousands of volts or tens of thousands of volts. Now, usually there will be another line of wires that are lower to the ground. They're still way up there that you can't reach them. And those are called distribution lines. And those are the power lines that usually are going to feed residential places like your house and so forth. And those are going to be, like in the United States, a common one is 7,200 volts, so, around 7 or 8 kV, less than 10,000 volts. And those are for kind of shorter distances. Those will transmit. They'll usually run those wires, along one street, like a couple of blocks. And every so often on a utility pole, you'll see this kind of giant paint can shaped transformer. And it's an oil-filled transformer. And inside of it, you have something like this, where you'll have, you have your top lead, which is your high tension coming in. And that's going to be that 7,200 volts. And then the bottom lead is going to go to a neutral. And the neutral bus is going a lot like down lower on the pole yet. So, and that neutral will actually have a bonding wire that goes down like this. And again, goes to an earth ground, like a ground rod. Okay, so the neutral and the ground are tied together here. And then your high tension line or distribution line is here. And then way up here, you would have your actual transmission lines. But not, in residential areas, you won't always see the transmission lines. Those are the ones that are for long distance transmission power. So don't worry about those right now. Now that voltage goes into a primary of a transformer. And then on the secondary, you have kind of a split winding, a center tapped winding. And this is for single phase, by the way. We're not going to talk about three phase. I don't want to confuse you on that. And what happens there is you have, this is high voltage in here. The output is going to be somewhere, is going to be from L1 to L2 is 240 volts. And then from either line to the neutral is going to be 120 volts. Okay? Roughly. And this can vary a little bit depending on line sag and different things like that. So it can go a little above that, it can go a little below that. And this is typically how it works. The neutral is going to be that center tap. We're going to call that neutral. And this is a split phase wiring. This is still single phase. I know it's confusing. You have 3 wires, but it's still called single phase. This is a split phase wiring topology. So this neutral is going to tie to the ground, okay, coming out of the pole, as is this, okay. And all this stuff, remember, is coming from your power plant on this end. That then goes into your house as 3 wires. Line 1, line 2, and neutral, or L1, L2, and neutral. And it goes into your mains panel, or your breaker box. And I'll get some pictures that I'll put up on the screen as I'm talking here. Inside the breaker box is where you have all the terminals for all your circuit breakers that control each of the circuits going around your house. And half of those circuits are connected from L1 to neutral. The other half are going from L2 to neutral. If you put a double circuit breaker, it'll go across these 2 leads and you'll have 240 volts. If you put a single position breaker, then then you reference it to the neutral, you have 120 volts. Now, getting a little bit closer, if you look at your mains panel, inside there, you have your neutral coming in and your L1 and L2. In the case of the ground, you have a ground rod at your house. And that ground rod comes up and goes to a bonded bus bar. And the only place that the neutral and the ground will be bonded together, will be connected common to the same connection point, is your main entrance panel to the house. Anything that goes out of there, you'll have 2 wires connected to the same place, but they'll never touch each other again for the rest of your house, if it's done right. One will be neutral, and that'll be like a white wire. The other will be your ground, and that'll be a bare wire or a green wire. And then your L1 is going to be a black wire. This is in the case of 120 volts. In 240 volts, you'd have another breaker, and they'd be connected together, and you'd have L1 and L2 and ground, and you would not use the neutral. But I'm not getting into that right now. We're just talking, just giving you a backstory here. So then that goes out to your outlet, which is this. And one side, which is your silver terminal, in this case, is going to go to your neutral. And this green terminal is going to go to your ground. And your gold terminal will be connected to the black, which is going to be your hot. Okay, so this is called hot. This is called neutral. This is just all basic stuff. Most of you probably already know this. Now in this outlet, if you notice, the ground is connected to this metal part, and this metal part is connected to the mounting ears of the outlet. So anything metal that touches these will also be connected electrically to ground, physically. See that? And this is important that I'm telling you this because you're going to see something different in my setup. Okay? Now, when we talk about a ground system and everything, and why this can be dangerous, let me show you what happens here. All right, I have my fluke meter connected to ohms, or it's set up for ohms, so you can see. And I don't even have this oscilloscope turned on. It's just plugged into the outlet, and it's plugged into another outlet in the back of my bench. So it's not even plugged into this outlet. But if I go from, and remember, this is where we plug our probes into. So here is, an oscilloscope probe. And you plug it into either here or here. If I measure from the outer part of the connector to the ground, I have a dead short. So essentially, when I plug my oscilloscope in using a 3-prong plug, anything connected to this terminal is going to be connected to all of the ground terminals in the house. In addition to that, if you look back down here, ground and neutral are bonded together in your mains box. So all the way through the ground, it'll come back to this bus bar, and anything connected to that terminal on my oscilloscope is also connected to the neutral of my incoming mains. Now, why would that be a problem? Well, this is where it gets interesting. So, again, when I plug my probe in here, if I go from the negative terminal of my oscilloscope probe to the ground, you see what's happening? Again, it's a dead short, or it's a connection. Of course, you see 1 ohm because there's a little bit of resistance in all the connections right now, but you get the point. So pretty much anything I connect this probe to, I am connecting to earth ground. That's the point that I'm trying to make. Now, I'm not wearing my mic, so if I knock it over and it gets banged around, I'm sorry about the sound quality. So here's where the problem comes in. If I connect this probe, this terminal here of my probe, to anything that is not earth ground, anything that is a different voltage than earth ground, I am now connecting that voltage directly to earth ground, causing a short. So, case in point, you have a radio, one of those transformerless ones, one of those All-American 5 radios, and it has a power cord that is non-polarized. And one of these lines is actually, in a roundabout way on these radios, quite often connected to the chassis. Actually, the better symbol would be, something like this. What do they do? Like that. So it's connected to chassis ground. That means this prong is connected to this radio, and if I touch this radio, whatever potential is on this power cord prong is now on my hand because I'm touching it. And here's the problem. These prongs are non-polarized, meaning you can see how on an outlet one prong is taller than the other. So if you have a polarized power cord, such as right here, you can see one's bigger than the other. See, this one's narrow, this one's wide, so it will only plug in one way, but it will not plug in this way. It won't fit. And that ensures that the same wire is always connected to hot and ground. So this is always going to be ground, this is always going to be hot, and the same thing goes with this. But in old power cords, and certain ones that are even made today, they're non-polarized, meaning both blades are narrow like this, so I can plug it in either way. So what happens if I plug this one, which should be the neutral, into the hot? I've now just put my 120 volts on this radio. And now if I touch that radio with this probe, I go to ground this, to go check things, I've just now connected my 120 volt mains through this little thin wire directly to ground. And this wire will blow up. It will just burn right open. This happens a lot. More importantly though, if you're touching something that's grounded, so you're touching this and you touch that chassis, you just put 120 volts or mains power through yourself. The same goes true in other countries that use 240 volts and so forth. It is still possible for that to happen, although their wiring in different countries is different than ours and makes it more difficult. So our wiring can be kind of sketchy here because of that. You have to be careful. So what people will do is they will put an isolation transformer between this plug and the mains. An isolation transformer is just what it says. You have a primary and a secondary, and it's a 1-to-1 winding. So whatever, it's 1-to-1, right? So if I put 120 in, I get 120 out. And here's the thing. This side, you know, your neutral's bonded to your ground and everything here, and your hot goes into here, just like that. But this side has no reference to the ground. So no matter which way you connect, you know, your plug, so you put your outlet here, and you put your power cord here, it doesn't matter which way around you put it, this chassis is never going to be electrically referenced to the neutral, and therefore it makes it more safe. It's not safe still totally, because you still have 120 volts inside the radio and you can still get shocked. But what it's going to prevent is it's going to prevent your test equipment or anything that's connected to neutral and ground from causing a ground loop and causing a short or making live mains on the chassis. I hope that makes sense. That's why we have an isolation transformer. Very, very important. Without this, you really can't use this. Okay, now there's things you can do called differential mode, or you could buy a differential probe for your scope, things like that, but not every piece of test equipment in existence has that. And not all test equipment gives you electrical isolation. You know, like oscilloscopes are, you know, are a really good example of that. So are spectrum analyzers. All those things, the negative terminal is connected to earth ground. It's just the way they're designed. Even this, you know, many thousands of dollars Tektronix scope, this is connected to ground. All of these probes, there's no isolation down there. So the way it works. Now, you might want to just go and purchase a transformer, you know, an isolation transformer. They come in a little metal box. They're all prefab. They have a power switch on them. You plug them into the wall, and then they have an outlet you plug your device into, and they're electrically isolated. But they really aren't. And I'll show you why here in a minute. If you look at the schematic of a commercially built isolation transformer, you do have a separate electrically isolated primary and secondary. You see that? So this is your line input. I don't know why they drew an outlet there. It should be your power cord. So ignore that. And then you have the output, which is where you plug your radio that you're testing. But because of the electrical code and so forth, especially like if you buy a hospital grade isolation transformer, you figure hospital grade, it's got to be higher quality. Well, no. What they do is they take this ground prong. So this is going to the ground in your power box, which by the way is bonded to the neutral, which is this one right here. So technically in your power box, this and this are tied together in your power box. Okay? So look what they've done. All the grounds are connected, and then they even go to the chassis of the little box that the thing's mounted in, and they ground it as well. And then there's a shield, which is fine. That's electrically isolated from all this. This is a noise shield. That's why they call it a Faraday shield. And they kind of defeat the whole purpose of what we're trying to do here for our purpose. While this does give electrical isolation here to here, this ground lead is now tied into here. Now, if you only plug something into these two pins, you have electrical isolation. But if you plug in, something that's a 3-prong plug, you've now just taken your isolation out of out of the equation. So typically, a modification you would do to these when you buy them would be to remove this portion of the ground wire, so that this is a no connection. And that ensures that you truly have an isolated secondary. Now again, with a 2-prong plug, this doesn't mean anything. Okay? The other thing is, some of these isolation transformers, depending on what they're designed for, will even have another bonding wire here. I've seen it. Not every one of them have that, but some of them do. Those are really bad because now you've just introduced the neutral line to here. So if you touch something to ground, you put your ground probe to something that's connected to this side, you've just introduced 120 volts between here and here across that ground lead, and you will cause a short. That's pretty uncommon for that to happen, but it can. So I always remove this wire. I'm not telling you what to do, okay? Safety is safety, but what you will find is people that use this on a test bench for testing radios and things that are hot chassis, they will modify their isolation transformer to remove this. Or they'll just use a transformer and make their own. Mine is a homebrew one, so I don't have to worry about any of this. I'll show you in a little bit. So that's what this is all about. So electrical isolation, that's what we want. Okay, so here's a really quickly drawn sketch of my bench, the way it's set up. We have L1 and L2 coming out of our mains box, that feeds the house. And I have 240 volts, ground and neutral, so I have a 4-wire system coming in. That goes through a circuit breaker, which is this sub panel down here. See it? Right there. And there is a it's a double pole breaker. And if either L1 or L2 has an overload, either with respect to one another or to the neutral, it will trip the breaker and shut off the whole thing. That's how that works. Now, the first thing this does is I pick off one of the lines and it goes into this outlet. The ground goes to the ground prong, the neutral goes to the neutral prong. It's the way it goes. And actually this should be a bigger, and I have it drawn upside down, but don't worry about it. And of course, in a perfect world, this should have its own separate breaker and all that stuff, but it doesn't. So again, this is a bench test piece of equipment. This is not a National Electrical Code house thing. This is for a test bench. It also feeds a 24-volt power supply, and more about that in a minute. From there, it goes into a big electrical contactor. I'll show you that in a minute. And an inrush current limiter, which is, again, a huge one. It's not the kind you're used to seeing. And this is necessary because the transformer I have is abnormally large. It's out of an X-ray machine, and it can deliver up to about 70 amps, I think, of current at 120 volts, and like 45 amps or something like that at 240 volts. So it's a very powerful transformer. That's why it makes so much buzzing noises you hear in the background. The price was right. I tore it out of an old machine we were scrapping, and I got it for free. Better than anything you could buy. So when I flip this toggle switch here, this little rocker switch, it turns on the coil for that contactor, pulls these in, and that powers up my isolated power. This outlet feeds all the outlets to the bench for the test equipment. So all the test equipment, everything plugs into this. My device under test will plug into these. So I have a direct isolated output, and you can see the ground is open. There's nothing connected to them. And they are isolated ground outlets, just like unlike this. In other words, they're those orange outlets, and the center prong does not connect to the tabs. Because if it did, when I put this in this position, it would then ground the panel that these are all screwed to, and by proxy these would all be grounded as well, and that would introduce a ground into here, which we don't want, in case you're testing something that uses a 3-prong plug. Now, when I turn this on, I have two different outlets. One is just direct 120 volts, and that goes to this power strip down here. You can see it. The other one goes to this outlet right here, and you can see it's orange, so none of the tabs or anything are tied to this prong. And it has its own little 10 amp breaker, and there's to turn it on, and there's the bypass, and then there's the 3 switches for the current limiting bulbs, and that is going to be the current limited isolated output, which is this one right here. So I have 3 bulbs, and they're all going from the one leg of the output through a bulb and through a switch. So if I turn all 3 of these switches off and I turn the bypass switch off, there will be no power going to this outlet. So as I switch these in, I put more and more load. These bulbs will be in parallel, allowing more and more load to go into the device under test. So I can limit the current a lot by putting one small bulb, or I could put multiple bulbs in parallel, which will allow more current to flow. In addition, I can hit this bypass switch, which is a 20 amp rated switch, and have a direct connection to this outlet. So that's what that is, and that's that big switch down here at the bottom. And that's how that works. So when you see this, that's my, in a nutshell, how it's wired up. I'll take a couple pictures and I'll put them up on the screen so you can actually look at it now. Okay, I'm going handheld, so I'm using the internal microphone here. And things are a little bit cramped back here, but here's the box that's on the back of the bench. And if we lift this off, I might not be able to get it off of here with one hand. Let me take this off. As you can see, there's this really big transformer in there. It is huge. It's hard for me to get it all in there. And it has its own fuse. That's kind of like a dead man fuse in case everything goes wrong. We got that. And that goes down into the control circuitry. Hold on. And taking this off with one hand reveals the mess that's in here. And you can see all the wiring coming in. And there's our outlets. There's the contactor with the 240 volts going to the transformer. There's the little power supply, and again, this all came out of a X-ray machine too. Here's the breaker, and that goes to this one over here. This is the direct one that has the ground and everything, and this is the isolated one coming out of the transformer, so all the isolated power. And it's kind of hard to picture it the way it's shown here, but that's how it's all wired. So the takeaway from this is make sure you don't get grounds and neutrals tied into your isolated output. Make sure everything has proper fuses and so forth on it, or breakers or whatever. I didn't show in here, but there's a breaker in there. You could see it. Again, I sketched this out very quickly, but you can see the breaker here. You can see the other breaker up there. I kind of showed you that. There's a breaker here. I have fuses. It is, and even that is not, everything. Another important feature, if you're going to work on electricity and work with things that could potentially cause a fire or something, make sure you have the proper, there's a fire extinguisher. I have several of them in here at different locations, easy to get to. I make sure they're good and they're up to date. Just whatever you can do. I try to stand on a rubberized mat, if you could see it down there, but try to isolate myself a little bit. And even with that, you have to be careful. Nothing takes the place of safety and thinking it through. If you're not comfortable with this sort of thing, you're not comfortable working with high voltages or dangerous voltages, don't do it. Learn a little more about it. Work with things that run on low voltages, things that are battery operated and so forth, until you get used to how electricity works. And even with that, don't become complacent, because just when you think that it's a routine to you and you've done, I've heard so many people say, I've done this for 30 years, for 50 years, I know what I'm doing. Well, those are the people that get hurt, is because you forget that you can still make a mistake. Everybody can. I've had some pretty bad experiences myself over the years. You're going to, if you're going to work in this field, eventually things will happen. But if you set yourself up properly, you can minimize it and at least ensure, or try to ensure, that if something does go wrong, it's not going to go really wrong. I've gotten across a 480 volt line. It doesn't feel good, but but always because of some of the practices I use, I survived it. It didn't even, I was able to just get up and keep working. It did knock me across the room, I'll admit it. It was one of those situations where it was a very complicated circuit, and it was one of those things where it had multiple power going into it from different sources. Even when you shut the breaker off and things, or shut the power off, it still had, there was areas that were still powered, because there was some special 24 volt supply that, for some reason, the way the circuit was designed, it picked it off of the 480 volt, and they did it through these resistors, and I got across some of that, and it bit me pretty good. I could tell you a lot of stories like that, but it happens. So don't mess with this stuff unless you know how to. And even when you know how to, be careful. That's all I can say. Nothing is worth your life. This is supposed to be a hobby. It's supposed to be fun. You're supposed to enjoy it. Make sure that's what it stays as, and not something that you forget about what this is really all about. So anyway, I hope that answers the question. And as always, I wish you all peace, joy, happiness, and good health in your lives. And I'm going to get back to this amplifier video.